In the previous video, we discussed about the bipolar junction transistor and in the base region how the minority carrier distribution behaves in the forward active mode that we discussed. In today's video, we are just discussing about the emitter region, and in the emitter region how the minority carrier distribution will behave, and exactly the same way we are going to derive the excess minority carrier distribution function from the ambipolar transport equation that we have already used. And we can start that from the same diagram, okay, for the forward active mode in BJT that we have already discussed. Okay, let's do that. So if you remember the distribution diagram, so this is basically NPN bipolar junction transistor. This is emitter region N, and this is the base region, okay, which is P, and we have the collector region, okay, which is again N. We will set the boundaries, okay, and suppose this is the boundary, the base region, okay, this base emitter region is forward biased, okay, in forward active mode, and hence the space charge width will be less as compared to this one, the base collector region, which is reverse biased. Okay, so now set the condition similarly here, the emitter region here, suppose this is the emitter region, and we got to name it. Let's say this is x equals 0 to x equals xb being the neutral base width, x double dash is equal to 0, and x double dash in this direction we can name for the emitter x dash equals 0 to x dash is equal to xe, right? So that's the emitter region, neutral base width, and here we got the x here, x is equal to 0 to x equals xb. Now in the collector region, which is a n region, the whole will be the magnetic carrier concentration, and let's say in the collector region the whole concentration at thermal equilibrium, let's name it as pc0, right? P for the whole concentration, C for the collector region, O for the thermal equilibrium concentration. Base collector junction is reverse bias, so this will be almost 0, like close to 0 concentration to reaches this pc0, right? And this region, base emitter region, is forward bias, so the magnetic carrier concentration or injection of magnetic carrier will be maximum. So from this it will come to, you have the thermal equilibrium concentration, let's name it as nb0, n being the magnetic carrier here in the base region or electrons, and in the base region thermal equilibrium, so it will come here to almost 0 here, because the base collector region is what is your reverse bias. So this will be the concentration, let's name the function here. This is nbx, okay, variation or the change in x. Here it is pc, the change in x double dash, right? And similarly in the emitter region, your n region, this will be also p as the magnetic carrier, and let's name it as pe0, thermal equilibrium. Now this is forward active mode, so the concentration will be more, but base is moderately doped, so the concentration will be little less as compared to the magnetic electrons from the emitter to the base. So it will go like this, and will reach to the thermal equilibrium at x dash equals xc. So this is our overall diagram. It's a repetition, we have done it in the base region. If you will understand this diagram, you'll get the idea of distribution, right? So we are looking at the emitter region only, so here our function is pex dash that we are going to study. Thermal equilibrium concentration is pe0, so at any point you want to find out the excess whole concentration in the emitter region, we have to take pex dash minus pe0 for any value of x dash, that will give us the excess whole concentration in the emitter region, which is we said delta pe, right? Okay, so after this we can start with the emitter region, the ambipolar transport equation that we have written already for the base region. Okay, so rewrite that for the emitter region, which is, you can write de del square upon del x square of the excess carrier delta pe x dash, okay, minus delta pe x dash or tau e0 equals 0. If you do not know what is de and tau e0, please revisit, okay, that will help you to understand. So basically this de is your minority carrier diffusion coefficient, right? In the diffusion mechanism we have already discussed this, right? So de is your minority carrier diffusion coefficient, coefficient. Okay, and tau E0 is our minority carrier lifetime. Okay, what is minority carrier lifetime? If you remember, before undergoing recombination, for what time it exists, right, in that region, that's your minority carrier lifetime. Okay, so this is our minority carrier lifetime. Okay, now let's name this equation 1. We may reuse it. Okay, similarly we can write the excess hole concentration as I have already told you, delta PE x dash. Okay, that is the excess carrier concentration at any value of x dash is given by PE x dash in the emitter region minus PE0, which is the thermal equilibrium concentration. So in this region you can see at any point if you will take, okay, this value, so whatever value of PE x dash you are getting, our minus this PE0 will give you the value of excess. Similarly at any point of x dash you can take that. Okay, so this will be our second equation. We may use it. Now as usual, the process is to write the general solution for this equation 1, right? So the general solution we can write for the equation 1 from in this form, del square by del x square of delta P x dash minus delta P x dash divided by tau E0 equals 0, where dE and tau E0 has specific value, constant value. So the general solution can be written for equation 1. General solution to equation 1 can be written as delta PE x dash is equal to some random constant exponential e to the power, we will write e to the power this way as you know, plus x dash upon LE. I will define what is LE plus D, some random constant. We will be able to determine the value of this C and D from the boundary conditions, exponential of minus x dash over LE. Right, now what is this LE here? LE is basically dE times tau E0, right? So this is the distance covered by the minority carrier distribution, by the minority carrier, okay, before its recombination. So the distance it will diffuse, right, into the other or the opposite concentration before undergoing recombination. Okay, so this is the neutral emitter length. Okay, I mean it is less than the neutral emitter length that we will consider. Well, using this, okay, now the excess magnetic carrier hole concentration, we will use the boundary conditions. If you see at x dash equals xe, we got the concentration is PE0, right? Okay, so that value we can substitute here at x dash equals xe, what is the value, and at x dash 0, what is the value? This value. Okay, if it is forward biased, we know that equation, diode equation, right, where we have already determined the concentration at the space width, exactly what is the value. So we will use these two values, right? So the two boundary conditions, first one, delta PE if I will consider x dash is greater than equal 0, okay, equivalent to delta PE at 0, basically x dash is equal to 0 here. If you will substitute this value in this equation, let's name it as equation 3, right? So x dash is equal to 0, right, or in I wrote x dash is equal to 0 or more than 0, if you will see, right, delta P at x dash is equal to 0, substitute this value. Okay, here you will see x dash is 0, this is 0, this is 0, then e to the power 0 you got, right, which is 1. So we can write that delta P0 is equal to C plus D, right? The exponential term became 1. So let's name that equation as 4, equation 4. Okay, now similarly we can write delta PE at x dash is equal to xe, neutral base neutral emitter width at the boundary. You can see that x dash is equal to xe here. Okay, you can see this value is PE0, right? So we can write that delta PE at xe, so which is delta PE at xe is equal to, substituting x dash is equal to xe only, right? In equation 3 we can rewrite C exponential of plus xe divided by le plus d exponential of minus xe divided by le right? Name this equation as equation 5. So two boundary condition, one at x dash is equal to 0, we got this, and another at x dash is equal to xe, we got this. So equation 4 and 5 are from the boundary conditions, right? Now this is what we can write, the delta PE when x dash is equal to 0. So x dash is equal to 0, which is this value. We can determine this from your ideal diode equation. Okay, base emitter junction is forward bias, is just like a forward biased PN junction, and we have already derived this equation earlier. We are going to use that value for delta P at x is equal to 0 or x dash is equal to 0. So we can write that as it is forward biased. Base emitter junction is forward biased, so your delta PE at x dash is equal to 0 equals basically PE at x dash is equal to 0 minus PE 0, right? This is for any excess carrier concentration. We can write delta PE x dash is equal to PE x dash minus PE 0. If you go back to this equation 2, so we just substituted x dash equals 0 there and rewrote that equation, right? Name it as equation 6. Okay, now delta PE at xe, if you see, delta P at xe is actually delta P at xe will be PE x dash at x dash equals xe minus PE 0. So this will give you PE 0 minus PE 0, right? So if I'll write it for the excess carrier concentration, delta PE at xe is equal to PE x dash is equal to xe minus PE 0. That gives me PE 0 minus PE 0, which is 0, right? So basically we got delta PE at xc, excess carrier concentration, is 0. Okay, let's take this another equation. Okay, now what you have, if you carefully see, we got the 6 7 equations, equation 6 7 and your equation 4 5, right, can be equated easily. So here you got delta P 0 is equal to C plus D. Now you got C plus D is equal to your C plus D is equal to delta P at 0 is equal to C plus D. Now delta P at 0 is this P x dash equals 0 minus P 0, right? This equation, okay, which is okay, I will just rewrite it because I need to use the equation at x dash equals 0 is P 0, okay, times exponential of EVBE divided by KT. This is the ideal diode equation that we got, right? This one, okay, PE 0 times exponential EVBE by KT and minus this PE 0, right? Where you can take the okay, so we can rewrite it. Okay, so that will be PE 0, taking common, you got exponential of EVBE over KT, this minus 1. Okay, let name this as equation 6, right? So that will be easier to equate it. Okay, now we have the equation. If you see, delta PE 0 is C plus D, so C plus D is equal to this equation. So the first one we got C plus D is equal to PE 0, okay, taking bracket, exponential EVBE over KT minus 1, right? This is 1, okay, and this is, let's write equation 8. So we combined equation 4 and 6. Now let us combine equation 5 and 7, which is C exponential of xe by Le plus D exponential of minus xe by Le is equal to delta P x dash is 0. This one, equation 7, right? So we can write that. So basically our equation will be C times exponential of xe by Le plus D exponential of minus xe by Le, right? This equals 0. this equals 0. So equation 9, 8 and 9 equation. Okay, now you need to solve it. This is easy to solve. You can see either multiply exponential xe by lb, this term here, right, both the sides, and then subtract it, find out the value of d, because this one will be cancelled, d will get. Otherwise you just multiply exponential of minus xe by le in both these sides, right, and then maxi the subject, you will get the value of c. Refer to the previous equation the same way. Okay, so equation these 8 and 9, if you will solve, then you will get the values of c and d, right. You will get the values of c and d. You'll get the values of c and d solving these two equations. Then once you get the value of c and d, just substitute. Okay, substitute in the equation, in the general solution. The general solution is your delta p x dash. Okay, delta p e x dash is equal to c exponential of plus x dash over le and plus d exponential of minus x dash over le, that you have already written in the general solution. Now you got the value of c and d by solving this. Substitute here, right, c and d, and then your final value you will get something like this: delta p x dash is equal to p 0. Refer to the base region magnetic area distribution to see how we have solved this. Okay, pe 0 exponential of e bbe divided by kt minus 1. Okay, sine hyperbolic xe minus x dash divided by le whole divided by sine hyperbolic xe divided by le. Okay, so this can be also considered when this xe by le, okay, is very small, or you can consider this excess concentration can be approximately linear with the distance. Okay, xe is very small, so in that case we can rewrite it as delta pe x dash, okay, can be approximated to pe 0 divided by xe exponential of e vbe divided by kt minus 1, okay, times xe minus x dash. Exactly the same process we have done in the previous video for magnetic error concentration. Okay, so if your xe is comparable to your le value, then this delta pe x dash, okay, shows an exponential dependence on xe, that is verified. Okay, so you got the in this region delta p x dash, how the graph behaves. Here you can